So most of us think a washing machine full of thick white bubbles means our clothes are getting this really deep clean.
Oh, yeah, that is a super common misconception.
Right, but your machine might actually be using those suds to build like a protective shield around the dirt on your favorite t-shirt.
Which is pretty much the exact opposite of what you want it to do.
Exactly. So welcome to today's deep dive. We are taking one of the most mundane chores imaginable, doing the laundry, and really breaking down the hidden physics, the chemistry, and even the economics behind it.
And we're pulling all of our insights for this session directly from the U.S. Department of Energy's official guidelines on appliance efficiency.
Which is fascinating because, when you actually look under the hood of how we wash and dry fabrics, you realize something pretty crazy.
What's that?
That relying on the habits our parents taught us decades ago might literally be costing a small fortune.
Oh, absolutely. And secretly destroying our wardrobes in the process.
Yeah, and even introducing some very real physical hazards into our homes.
The gap between how we think these machines work and the actual, well, the fluid dynamics happening inside them is massive.
It really is.
Because the Department of Energy, they aren't looking at laundry from a marketing perspective.
Right, they don't care about selling you soap.
Exactly. They are measuring the raw electrical draw, the chemical realities of modern detergents, and the massive impact those two things have on the national power grid.
So to really understand that impact, we have to look at the very first decision you make at the control panel.
Right, before a single piece of clothing even gets agitated.
Temperature dial.
Ah, yes. The famous temperature dial.
I mean, the data here is just wild. It shows that simply switching the temperature setting from hot to warm can cut a load's energy use by 50%.
50%, and dropping it to cold saves even more than that.
Which is crazy to me. I mean, I've always just assumed the violent spinning and like the heavy motor churning the water around was what pulled all the electricity.
Yeah, that's what most people think, honestly. It makes intuitive sense when you hear the machine working so hard, but that motor actually draws a surprisingly small fraction of the total power.
Wait, really? The spinning is the main drain?
Not at all. The real energy sink is thermal mass.
Okay, thermal math. Break that down for me.
So water is incredibly heavy. It's about 8 pounds per gallon.
Right, that adds up fast.
And it takes a tremendous amount of electrical or gas energy to raise the temperature of 20 or 30 gallons of water by, 40 or 50 degrees.
So when you select hot, you're basically...
You are essentially asking your appliance to act as an industrial water heater for an entire hour.
Wow. But see, we've been conditioned to view hot water as, like, the ultimate sterilizer.
Oh, for sure.
Whether we are boiling water for pasta or scrubbing greasy pots in the sink, heat equals clean in our minds.
It's a deep-seated psychological link.
It is. It feels incredibly wrong to throw a pile of sweaty gym clothes into freezing cold water and expect them to come out smelling fresh.
And that psychological hangover comes from a very different era of chemical engineering.
How so?
Well, decades ago, powder detergents literally relied on thermal energy to melt the fats and dissolve the harsh chemical surfactants.
Oh, so the water actually had to be hot for the soap to even work.
Exactly. If you used cold water in, say, 1985, you'd end up with powdery clumps glued to your jeans and stains that wouldn't budge. The heat was doing the heavy lifting.
Right, but modern detergent chemistry has bypassed that.
Completely bypassed the need for thermal energy.
Okay, so how does that actually work on a molecular level? Like if the heat isn't melting the dirt away, what is the cold water doing?
It's all about biological catalysts, specifically enzymes.
Wait, like biological enzymes?
Yeah. Modern cold water formulas contain highly specialized enzymes, things like lipases, which target lipids and fats,
Okay.
and protease, which break down protein-based stains like sweat or blood. These enzymes are essentially molecular scissors. They're designed to seek out specific types of grime and literally snip the chemical bonds holding them to the fabric.
That is wild.
And crucially, they are engineered to activate and thrive in cold environments, usually right around 60 degrees Fahrenheit.
Wait, if they are specifically engineered for cold water, does that mean using hot water might actually be counterproductive?
In some cases, yes.
Like, are we cooking the enzyme?
You actually are. Excessive heat can denature certain enzymes, changing their physical shape so they can no longer lock onto the dirt molecules.
Oh, so like how cooking an egg permanently changes the structure of its proteins.
That's a perfect analogy, unless you are dealing with heavy, Saturated mechanical grease or literal motor oil, heating the water is not only pouring money down the drain.
You might actually be neutralizing the very chemistry you just paid for in the detergent aisle.
Exactly. You're sabotaging your own soap.
Okay, so we've optimized the water temperature. We eliminated that massive electrical draw.
Right, which brings us to what's physically happening inside the drum.
Yeah, the load logistics and the chemistry of the suds. The guidelines advise washing and drying full loads whenever possible to really maximize efficiency.
Yeah, or at least strictly matching the water level setting to small loads if you can't fill it up.
Right. But they also highlight a very specific rule for the soap itself.
The high efficiency rule.
Yes. If you have a front-loading washer or a high-efficiency top loader, you absolutely must use detergent explicitly labeled for high efficiency, or HE.
Because high efficiency machines operate on a completely different physical principle than older models.
Right. The older ones were the ones with the big plastic post in the middle, right?
Exactly. Traditional agitator washing machines filled the entire tub with maybe 40 gallons of water and used that central plastic post to violently twist the clothes back and forth.
But HE machines don't do that.
No, they use a fraction of that water. They rely on gravity. The drum spins, lifting the heavy, wet clothes out of the shallow pool of water at the bottom and then drops them.
So they just repeatedly slap the clothes against the water and against each other.
Exactly. That mechanical friction, the physical impact of the fabrics colliding, is what physically knocks the loosened dirt out of the fibers.
Once the enzymes have snipped the bonds.
Right. The friction is the actual cleaning mechanism here.
Which brings us back to the suds. The American Cleaning Institute data cited by the DOE explains that HE detergents are specifically formulated to be low sudsing and quick dispersing.
Yes. And this is a hard thing for people to accept.
Oh, totally.
Mm-hmm.
From bubble baths to dish soap, we're completely conditioned to want a thick layer of foam.
We really are. Seeing a washing machine full of bubbles makes you feel like the clothes are getting scrubbed.
It feels entirely counterintuitive to intentionally seek out a low sudsing detergent.
But those bubbles are just trapped pockets of air. They contain zero cleaning power.
Zero.
None at all. The surfactants in soap work by having one end of their molecule attract water and the other end attract oil.
So they just pull the dirt away from the fabric.
Exactly. Foam is merely a byproduct of that chemical process interacting with air. When you use a traditional high-sudsing detergent in a high-efficiency machine,
You generate a massive volume of foam inside a very small amount of water.
right, and that foam acts as a physical barrier.
Wait, really?
It acts exactly like a system of tiny airbags.
Tiny airbags inside the washing machine.
Yes. When the drum lifts the clothes and drops them, they don't slap against each other. They land on this dense cushion of bubbles. You are effectively neutralizing the gravitational impact required to knock the dirt loose.
The garments just kind of glide over each other.
Precisely.
So you're paying for a machine that cleans through impact, and then you're unintentionally installing shock absorbers to prevent that impact.
That is a perfect way to put it. And on top of sabotaging the mechanical action, the low water volume in HE machines makes it physically impossible to rinse all those excess suds away.
Oh, because there isn't enough water to wash the soap out.
Right. The cycle ends, and you are left with a microscopic layer of soapy residue baked into your clothes. Ugh, that sounds awful. It is, because that residue is incredibly sticky. As you wear the clothes, it traps dead skin cells, environmental dust, and new sweat.
Is that why improperly washed clothes sometimes develop that lingering, musty odor even after they've been laundered?
Yes, that is exactly why. Precision dosing with low sudsing detergent guarantees the mechanical friction works and allows the water to actually rinse the fabric clean.
Okay, so we've relied on modern enzymes and mechanical friction to get the clothes perfectly clean using cold water.
But that immediately introduces a massive new physics problem.
Yeah, we now have a drum full of freezing cold, heavy, wet fabric.
And we somehow have to get it perfectly dry without ruining the material or wasting massive amounts of energy.
The dryer is, it's an entirely different beast when it comes to thermodynamics and home maintenance.
It really is.
The guidelines actually recommend separating heavy cottons, like thick bath towels, into a different load from lighter weight items, like t-shirts or synthetics,
Right, because of the risk of overdrying.
which they strongly warn against. If your machine has a built-in moisture sensor, they insist you use that setting.
Yeah, rather than just twisting the dial to 60 minutes and walking away, mixing heavy towels with light t-shirts forces the machine to compromise.
Because the t-shirts might be bone dry in 20 minutes.
Exactly, but because the heavy towels are still damp, the machine just keeps blasting heat for another 40 minutes.
What actually happens to the fabric when we subject it to that unnecessary heat? I mean, I always just assumed it got warmer,
Well, it begins to chemically degrade.
chemically.
Yeah. Cotton and synthetic fibers retain a certain amount of natural moisture that keeps them flexible. When you push past the point of dryness and continue to bake the fabric, the heat attacks the polymer chains directly.
Oh, wow.
The fibers become brittle, they lose their elasticity, and they actually begin to snap.
Wait, so that lint in the screen,
You aren't just looking at dust, you are looking at the disintegrated remains of your wardrobe. Excessive heat literally tears your clothes apart at the microscopic level.
that hurts to hear. But a moisture sensor prevents that by detecting exactly when the water is gone. How does the machine actually know?
Most sensors are surprisingly simple. There are two small metal strips inside the dryer drum.
Okay.
When wet clothes tumble across those strips, the water in the fabric conducts electricity, completing a small circuit between the two strips.
Ah, I see.
As the clothes dry out, there is less water to conduct the current, and the electrical resistance goes up. The computer monitors that resistance, and the moment it drops below a certain threshold,
It knows the fabric is dry and cuts the heating element immediately.
exactly, saving the clothes from that destructive baking phase.
But the compounding heat damage doesn't just ruin the fabric. It creates this highly flammable dust that gets pushed straight into your lint screen and the exhaust vent.
Which brings us to the most alarming part of the DOE guidelines.
Yeah, the maintenance rules to prevent massive fire hazards.
Yeah.
You have to clean the lint screen after every single load.
Every single one. And periodically vacuum out the slot below the screen.
But the biggest warning involves the venting material sitting right behind the machine. The guidelines explicitly warn against using flexible plastic accordion venting tubes.
That venting material is perhaps the most widespread hidden danger in modern households today.
It's wild to think that the cheap, flexible plastic accordion tube sitting behind millions of dryers isn't just inefficient, it's a literal fire hazard waiting to collapse.
People buy them because they are cheap and they easily bend when you need to shove the dryer back into a tight laundry closet.
But the ridges in that accordion shape are like a fluid dynamics nightmare.
A total nightmare. A dryer's core function relies on rapid, unimpeded airflow. It pulls room temperature air in, heats it up, evaporates the water from your clothes, and then has to push that incredibly humid, hot air out of your house.
Okay.
When you use an accordion tube, those interior ridges create turbulence. The air doesn't flow smoothly, it tumbles and swirls.
And that turbulence causes a drop in air pressure.
Exactly. Which means the heavy, wet lint falls out of the airstream and gets trapped right in the ridges of the plastic.
And as that lint builds up, it slowly chokes off the exhaust pipe. The machine literally can't exhale.
And then the blower motor has to work increasingly harder to push the air through a narrowing tunnel that uses more electricity, but more critically, the heat has nowhere to go.
The internal temperature of the entire appliance just skyrockets.
You now have a scenario where you are combining trapped, escalating heat with a plastic tube lined with highly flammable, bone-dry fabric dust.
It is a perfect environment for a spontaneous ignition.
This is exactly why manufacturers and the DOE insist on rigid, smooth-walled metal venting.
Because it maintains its structural integrity.
Right, and the smooth walls prevent turbulence so the lint stays airborne, safely channeling the hot air all the way outside.
There's also this great simple efficiency tip mentioned in the guidelines to capture the heat we've already generated.
The cool-down cycle.
Yes. Instead of running the high wattage heating element right up to the very last second of the timer, the machine turns the heater off a few minutes early.
And it just tumbles the clothes in the residual heat that's already trapped inside the drum.
It's capturing energy you've already paid for and putting it to work, instead of just blowing it at the exhaust vent.
Upgrading your venting prevents fires and speeds up traditional drying, for sure. But if we really want to stop wasting heat, we have to rethink how the machine handles the air itself.
Right. At a certain point, the hardware is the bottleneck.
Oh, absolutely. If you're running a washer and dryer from 20 years ago, behavioral tweaks are only going to get you so far.
The data on appliance upgrades is super compelling. Energy Star certified clothes washers use nearly 35% less water and 25% less energy than standard models.
And conventional Energy Star dryers use 20% less energy.
But the true paradigm shift the DOE points out is upgrading to an Energy Star certified heat pump dryer.
Those are incredible.
The guidelines state these machines can save a massive 20 to 60% more energy than conventional clothes dryers. The mechanics change entirely.
Because conventional dryers are essentially brute force machines.
Yeah, imagine trying to heat your living room in the dead of winter, but you leave all the windows wide open.
That is exactly what it's like. You are constantly pulling in freezing outside air, paying to heat it up, and then watching that expensive heat just immediately drift right back out the window.
It's a constant linear waste of thermal energy. Normal dryers pull in 70-degree room air, heat it to 150 degrees, blow it through the wet clothes, and then instantly blast that expensive humid air straight out the side of your house.
You're just paying to heat the neighborhood.
Exactly. Upgrading to a heat pump dryer sounds like trading in a gas-guzzling SUV for a highly efficient hybrid vehicle. The mechanics change entirely to prioritize efficiency. It's a closed loop, right?
Yes. Think of a heat pump dryer like putting a dehumidifier inside a closed sauna.
Okay, I can picture that.
It doesn't vent outside at all. It heats the air to absorb the moisture from the tumbling clothes, but instead of blowing that humid air outdoors, it passes it through a specialized cooling coil.
So it cools the air back down.
Right, which causes the water to condense into liquid, and that liquid just safely drains away into a pipe or a collection tank.
And because it's a closed loop, it takes that exact same dry air, reheats it, and sends it back into the drum.
It recycles the air continuously. It isn't constantly pulling in fresh air and heating it from scratch minute after minute.
Yeah.
By capturing the heat, extracting the water, and reusing the thermal energy, you completely eliminate the massive electrical draw of a traditional heating element.
That elegant physics solution is what drives that 20 to 60% reduction in energy consumption.
Exactly.
That is an incredible piece of engineering. But let's look at the economics of this for a second. Upgrading to heat pump technology requires a significant upfront investment.
It does.
For someone staring at the price tag of a new heat pump dryer, the immediate reaction is usually sticker shock.
The initial purchase price is absolutely higher. But this requires a shift in how we view household appliances. You aren't just buying a machine, you are securing a long-term reduction in your monthly overhead.
Right, the ROI.
Yes. When you cut your water heating costs by 50% by switching to cold cycles, reduce your total water volume usage by 35% with an HE washer, and then slash your drying electricity by up to 60% with a heat pump.
Those monthly utility savings quickly compound.
The machine essentially pays you back over its lifespan.
And that ROI calculation doesn't even factor in the extended lifespan of the wardrobe itself.
Very true.
Because these highly efficient machines use targeted moisture sensors and significantly gentler operating temperatures, the fabric isn't being cooked into brittle lint.
You aren't replacing faded jeans, stretched out shirts, and frayed towels nearly as often. The financial protection applies to both the utility bill and the physical items you are washing.
And it's probably worth noting the ultimate efficiency tip the guidelines provide. Sometimes the best machine is no machine at all.
Oh, absolutely. Taking advantage of indoor drying racks or outdoor clotheslines completely eliminates the dryer's energy footprint.
And it subjects the fabric to zero mechanical or thermal wear. We started this deep dive talking about how easy it is to just let muscle memory run the show.
Yeah, doing laundry on autopilot. We just throw the clothes in, pour a random glug of highly sudsing soap into hot water, and blast the whole load with intense heat for an hour.
But when we actually break down the chemistry of enzymes, the physical cushioning effect of suds, the compounding damage of overdrying, and the sheer fluid dynamics of a blocked plastic vent,
It becomes incredibly clear that operating on autopilot is a remarkably expensive and risky habit.
it takes conscious effort to step back and analyze a routine we've performed thousands of times.
Trusting the cold water chemistry to do the work and ensuring our exhaust systems are physically safe requires a slight behavioral adjustment, but the return on that minor effort is immediate.
It really is. And when you scale these individual habits up, the implications are staggering. Consider the millions of households running laundry cycles every single day across the country.
Think about the sheer volume of electrical wattage and natural gas being pulled from the national energy grid solely to heat millions of gallons of water, just to wash lightly worn t-shirts.
Or the energy wasted forcing blower motors to push air through collapsed, lint-filled plastic tubes. We often talk about energy conservation as this massive, abstract infrastructural problem.
Involving power plants and sprawling power lines.
Exactly. But it turns out A massive leap in how we manage our national grid and our own wallets might actually begin with simply turning a single dial to cold in our own laundry rooms.
It really makes you think about your next load of laundry differently.
It definitely does. But it also leaves me with one final thought to mull over. We talked about how the heat and friction literally tear your clothes apart, creating all that lint.
Right, the disintegrated wardrobe sitting in your lint screen.
But not all of it gets caught in the screen, right?
Yeah.
A lot of it gets blown out the exhaust vent or washed down the drain in the washer.
Oh, absolutely. Microfibers.
Exactly. So every time we do laundry, we aren't just wearing down our clothes. We might be silently coating our neighborhoods and waterways in millions of microscopic synthetic fibers. Makes you wonder if the next great leap in appliance technology won't be about energy efficiency at all, but about figuring out how to capture the invisible pollution we're washing away every single week.
That is a fascinating and kind of terrifying thing to think about.
So definitely something to keep in mind the next time you hear that buzzer go off. Thanks for joining us on this deep dive, and we'll catch you next time.